Do you see the presentation there?
Yes.
Okay. So my name is Xavier Calbet. I'm from the Spanish Met Service, IMET. And I will talk about towards a consistent multi-sensor QPE, and in particular the nowcasting SAF satellite QPE, and something we're building, a very simple IMET multi-sensor QPE to use for flash flooding. Here are the other co-authors, and yeah, we can proceed. So I will present a mixed thing. So as you can see here, different things, different topics. So I start with the nowcasting SAFs QPE, which is the CRRPH. And then I talk a little bit about inconsistency between satellite and radio QPE. And also what we're working on to search for this consistency between both measurements. And then I will briefly mention IMET's multi-sensor QPE and some words about the future. So we'll start with the nowcasting SAFs QPE. Right now we have 3 convective rainfall rate products. One of them is called CRR, convective rainfall rate. It's maintained, but with no development. The latest version is 2018. And then we are developing on the new products, which are called convective rainfall rate based on physical properties, CRRPH, and these are actively developed. Latest version is 2018. And the next version of the CRRPH will be based on principal components, which in this presentation I will call CRRPH PCA, just for the sake of differentiating it from the current operational CRRPH. And it's being tested as a prototype, and the developer is Jose Alberto La Huerta. And this is the one I will show here, just to be brief. Okay, so this new prototype was based on principal component analysis. As you probably aware, principal component analysis is a statistical method of reducing dimensionality of a specific data set. So what we do during daytime, the inputs we use are the infrared and visible channels, as you can see here, and also the cloud water path, which is calculated as 2/3 of the cloud optical thickness times the effective radius, which is obtained from another nowcasting SAF product, Cloud Macrophysics nowcasting SAF product. Okay, if you do a principal component analysis of these channels and parameters, we find that the first 2 principal components explain like 95% of the total variance. So these are the ones we are using for the generation of the products. So the next thing we do is we plot the 90% percentile of the collocated radar rainfall rate as a function of these 2 first principal components. And we get something like you see here. So this is the 90% percentile of the radar rainfall rate versus PC1 and PC2. And we transform this into a lookup table, and this lookup table is where we derive the product from. Okay, these are some results, daytime results, comparison with radar. So you can see to the right you have the radar, to the left you have the new prototype product. And you can see that they compare quite well. This is one day. And then during nighttime, we're planning to use exactly the same lookup table as daytime, such that we do not have big discontinuities between nighttime and daytime. But of course, during nighttime, we have no visible channels and no cloud water path. They're not available because there are no visible channels are not available. So what we're doing is we're predicting these 2 channels or these 2 parameters obtained from the visible from the actual inputs. The actual inputs, as you can see down here, are the infrared channels. So here you have an example of measured visible 06 to the left and simulated visible 06 to the right. You can see they compare generally quite well. Okay, so we obtain the product, same as before, we obtain the product for nighttime, and here are some comparisons. Here are actually all 3 versions of the CRR. So the regular CRR on the top left, the CRR PH version 2018 top right, and the new prototype on the bottom left. and the radar rainfall rate on the bottom right. You can see that the new product improves significantly on the other ones. Same for another case. You can see also how the new prototype improves a lot over the other ones. Okay, we did some statistics, and you can focus on the red numbers here. The probability of detection has gone up quite significantly from previous products, and the false alarm rate has dropped down significantly from previous products. So it is quite a big improvement from previous products. So at some point we will put this product operationally, and this will be the operational nowcasting SAF convective rainfall rate product. Okay, now let's talk a little bit about inconsistency between satellites and radar QPE. I think this is known by everybody. This is an example. Beware here that both scales are different, so the colors do not correspond exactly. But anyway, to the left you have the CRR-PH, sorry, and to the right you have the radar rainfall rate. And you can see that if you plot one on top of the other, this is close to Trieste. You can see that the overlap is not exactly the same, the quantities are not exactly the same, and so on. Why is it important to have these two products consistent? Because in many countries, in many places, you want to merge both data sets, both QPEs, radar and satellite, because not all countries have a complete satellite coverage. One of the clear examples is Australia. But there are many examples also over the ocean. There's no radar coverage, so you would want to complement with satellite data. Okay, so what we're working on is we're trying to search for consistency. So we're trying to find if there are any physical or measuring principles behind the inconsistency between these two measurements. This is in the very early stages, so I'll just show a few ideas here. Not only the signals should be measured, but also some kind of uncertainty or probability such that we can merge both data sets properly. And also perhaps a long-term goal would be also finding the dynamics of convection. I'll talk a little bit about that here. In the meantime, since we haven't reached that point, we just merge the data set the best we can, as I will show later, or just plot both products on different layers. Okay, this is what we're doing. We're trying to see if the environmental winds obtained from NWP, SIMWF in this case, affect the difference in the positioning of the radar precipitation, which is shown here in red, and the satellite precipitation in green. So this is an RGB with those two colors. And you can see that they do not match exactly, and we're trying to see if the NWP vertical velocity fields have anything to do with this displacement. There's some interesting things coming up also from the high spatial and temporal resolution new generation of satellite images or imagers. One of them is quite interesting, is done by Apke et al. And you can see how he derives winds from the top of the convective cloud. And from that, he can derive vorticity or convergences and so on. I think this can be very interesting to try to figure out the dynamics below the cloud, which can help us also understand what's going on and perhaps also detect or spot the differences between radar and satellite QPEs. I have to press here, otherwise oops, sorry. Okay, and then another work that is done by Sam van den Ecke is doing very, very simple models of updrafts and anvil expansion to derive also some properties. So perhaps this is a field we can exploit in the near future. I don't know, we will see how promising or non-promising these things are. Another thing I want to draw the attention to is that we're seeing from the measurements of temperature and water vapor some interesting features I will try to show here. So what I'm plotting here in the center is what the fluid dynamics people call structure function. So I plot here on the x-axis the effective distance in a log scale, and the vertical axis the difference squared of a parameter, in this case temperature and humidity, between 2 points, okay? And you would probably expect this to be an increasing curve to the right, from very low values to very high values to the right. But as you can see, this is not what's happening. What is happening is you have an increase, a very, say, quick increase in the smaller scales, and then it drops down, and then it increases again with the higher scales. I identify this with turbulence, actually, different scales of turbulence. So the first scale, which has a very, as you can see, has a very nice slope of 2/3, is called the inertial range. And then the other more extended range I call synoptic range from meteorology. Why is this important? This is important because the fields are very different. So in the synoptic range, we have a more or less smooth field. This is scales on the average greater than 10 kilometers. You have a very smooth field. This is the field we're usually used to look at, you know, on television, on weather charts and so on. But on the smaller scales, we have a turbulence regime, an inertial range turbulent regime. And this is scales approximately less, on average, again, less than 6 kilometers. And what you don't have something uniform like you have in the other range, but you have something like, looks more like a random Gaussian field. So it looks more like this plot you have to the left here. Cynthia just showed some examples of that, where of course, in reality, you don't get a perfect random Gaussian field, but you get something similar. Okay. And then I will talk a little bit about the AMETS multisensor QPE. This is a relatively new thing we're doing, also relatively simple. It's developed by Peyo Oria. And what we're doing is we're using kriging with external drift, with rain gauges, satellite and radar data. Okay, we try to merge all those three, since we cannot merge them, say, in a consistent fashion. We just try to merge them as we have them. And so it's using as input data, rain gauges from different networks, and also some of them from crowdsourcing. We also use the radar fields, precipitation fields, and also satellite-based product, in this case, the CRRPH, not the prototype one, the operational one we saw before. So we just do a kriging with external drift, and we compare with the rain gauges, and we take whichever instrument is measuring best. So if the radar is measuring best relative to the rain gauges, we take the radar. If the satellite is measuring better, we take the satellite, and if both are measuring well, then we take both, all three, I should say, if you include the rain gauges. Okay, so this is a case study we did, and it reproduces quite well the precipitation. In this case, this was a flash flood event, actually. Okay, here are some results for a particular day, chosen at random, and you can see to the left here that the rain gauges results are quite similar between the optimal estimation or KED estimated, QPE estimated, and to the right you have different results for different spots. Sometimes the radar data is more valuable, sometimes the satellite data is more valuable, sometimes both are more valuable, and they can complement very well the rain gauges. Okay, and that I now come to the conclusion, to the future. Well, we know this is a problem forecasters have, or nowcasters have. There are too many products for a forecaster. So we need to simplify or combine these products. As you can see, this is not easy. And I think a previous step before combining products is trying to find the consistency, and also probably determine the uncertainties or using probabilities of these measurements. In the meantime, the nowcasting staff is making a big effort in making software available to plot all the data together. So this is the alternative solution, plot the data together. This is an example. So we're basing our plotting, we're supplying our users with plotting tools using the Adagug viewer. you have the link down here, and you can see here several different products plotted one on top of the other, on top of a nice map. As I say, Adaguk is developed by KNMI. As you can see, you have the website here if you're interested. It has some very nice features, so like web mapping services, opened up, and so on. So summary, we think merging appropriate plotting of products will be key in the future. We're working toward that goal. You can see the products in real time in the Adaguk viewer here. More information on nowcasting soft products you can obtain here. And we're also making a big effort to generate the products and also tools to use open source software to display them. So in this case, it's Adaguk. And I think it's important that we keep in mind, I think this is quite important, it was discussed a bit before, but it would be beneficial for the whole community, especially for small countries who don't have the resources to do this big research projects, to have a common development platform for nowcasting, and it should be based on open source software. So Adaguk is a clear example. We saw PySteps before, it's also a nice example. The nowcasting soft products are not completely open source. You do have the source code available. We're working towards that, and we hope this will change in the future, and we will have a more collaborative and more open development. Okay, thank you.
Okay, thanks a lot for the nice presentation. So we have a question on Slido from Clemens Zimmer, and he asks, which observables dominate PC1 and PC2?
That's a good question. I don't have an answer for that right now. It's a combination of several channels and the cloud water path, but I don't have the exact weights. I can look it up if he's interested, but it's a combination of all of them. So it's not just a few of them.
Mm-hmm. Okay,